Here we have two vectors a and b. We want to get a dot b. Well, we just multiply the I components together, 2 times 3, and then the j components together, minus 5 by plus 2. So we get 6 minus 10, which is minus 4. Notice what we get if we calculate b dot a. So we take the I component of b and multiply it by the I component of a. Well, that's just 3 times 2, which is the same as 2 times 3. And of course the j components multiply to give minus 10. So we get the same answer. And we saw before that indeed the scalar product of two vectors is commutative, because the magnitude of a times the magnitude of b is the same as the magnitude of b times the magnitude of a. Now, since the dot product of these two vectors came out to be negative, that tells us that this angle in here must actually be greater than 90 degrees, because the cos of an angle that lies between 90 degrees and 180 degrees is negative. In the next example, we are going to get the angle between vectors p and q. So let's look at the dot product. Well, we multiply the I components together. 3 by minus 4 is minus 12. The j components give us minus 1 by 6. So we get minus 18. And of course, the definition of the dot product is that it's the product of the magnitudes of the vectors by the cos of the angle in between the two vectors. How do we get the magnitude of p? Well, we just square the components and sum them. So we've root 3 squared plus 1 squared. That's root 10. The magnitude of q is root 4 squared plus 6 squared. That's root 16 plus 36. That's root 52. So we can calculate cos theta from this. So to one decimal place we get 142.1 degrees. So here's a rough sketch, and you see we have indeed an angle between 90 and 180. So that's why we get a negative value for the cos of that angle. The 18 in the dot product refers to the length of the projection of one vector onto the other. Well, actually it's the length of the projection. Say if we project this vector onto the line joining this one, is the length of this line here multiplied by the length of this vector. Next, we want to use the definition of the scalar product to show that if two vectors are perpendicular, their scalar product is 0. Okay, so let's call the vectors a and b. Well, then a dot b is just the magnitude of a times the magnitude of b times the cos of the angle in between them. Well, if they're perpendicular, the angle between them is 90 degrees. Now, since the cos of 90 degrees is 0, all of this is going to be 0. So the dot product or scalar product is 0. So, if we think in terms of projections, b cos 90 is the projection of vector b onto vector a. We project the tip of vector b at right angles to vector a, and of course the length of the resulting component is 0. If a and b are perpendicular vectors, simplify this here. Well, if they're perpendicular, we know that the dot product is going to be 0. Okay, we saw in a previous video that the dot product is distributive over addition of vectors. So we can take vector a and distribute it into this sum here. So we have a dot 3a. And then we can take vector a and dot it into this, and we can take the scalar 5 to one side, 5a dot b. Then we have minus 2b dot 3a. Well, that's going to give us minus 6b dot a actually. Then we have minus 2b dot plus 5b. That's going to give us minus 10b dot b. So we can always put the scalars together as we've seen before. Okay, now what is vector a dotted with itself? Well, if we go back to the definition of the dot product, it's the magnitude of the two vectors multiplied by the cos of the angle in between them. Well, the angle in between vector a and itself is 0, and the cos of 0 is 1. So we've the product, we've the magnitude of a times itself. That's the magnitude of a squared. So this term here is going to be 3 times the magnitude of a squared. What about a dot b? Well, that's 0. b dot a is also 0. And then we have minus 10 times the magnitude of 10b squared. Now if we want to, we can write this as 3a squared minus 10b squared. We can just leave off the underline to indicate the magnitude. So the magnitude of vector A is A without the underline. Now P and Q are vectors in 3 dimensions. To get the dot product, we just multiply the corresponding components. So the I component of P is 1, so we have 1 times the I component of Q, which is 3. Then we have the I component of J, which is 8, times the J component of P, which is 8, times the J component of Q, which is minus 2. Then we have the K component of P, which is 7, multiplied by the K component of Q, which is 5. So we calculate all of this to get 22. Next we will show that these 2 vectors are perpendicular. Well, we just take the dot product of them. So we multiply the I components, 1/2 times 2, then multiply the J components. So the J component of this vector is plus 1, the J component of this vector is minus 1. So you see we get 2 minus... we get plus 1 minus 1, which is 0. So if the dot product is 0, as we've seen before, then the vectors are perpendicular. The work done by a force F in moving a body through a displacement r is given by F dot r. So we want to find the work done by this force F if it causes a body to move from the point 112 to the point 735. So the work done by the force F on, say, this particle here, as the particle moves from here to here, is the component of the force F in the direction of motion of the particle. Well, that's the magnitude of force F times the cos of theta. And then we multiply that by the distance through which the particle moves. So that distance is the magnitude of this vector here. The magnitude of r is just r without the underline. But of course this can be written as f r cos theta. That's just the definition of the dot product of vector F with vector r. It's the magnitude of F times the magnitude of r times the cos of the angle in between them. Now, by the way, we are assuming here that F is a constant force. So as the particle moves from here to here, F doesn't change. So when the particle is, say, here, the force acting on it, well, the force F hasn't changed. So it looks like this. This vector is the same as this vector. Now, of course, the reason for the particle moving from here to here, we don't know. There could be many forces acting on this particle. F is not the only force acting on it. Well, it could be the only force acting on it. The particle could have been moving already, so its inertia keeps it going in this straight line. But, well, that's unlikely, because then the particle would move in a curve if F is acting on it to pull it out of this straight line motion. So in general, we have many forces acting on this particle. However, the particle does move in a straight line from here to here. The displacement vector is r. So we're only getting the work done by this force. We're not thinking of any of the other forces involved in the motion of the particle. So the work done by the force vector F is F dot r, assuming that F is constant as the particle moves this distance and in this direction. So that's the background. So we can connect the idea of the work done by a force to the dot product of the force vector and the displacement vector. So in this example, F is 3i plus 7k. Now what about the displacement vector r? Well, the body moves from 112 to 735. So to get the displacement vector, we have to get the final position of the body minus the initial position. That's 112. So we just subtract corresponding components. 7 minus 1 is 6, 3 minus 1 is 2, 5 minus 2 is 3. So here is the displacement vector r. Now, by calling it 6, 2, 3, it means that if we move this vector so that its tail is at the origin. Now I'm not going to show this accurately. If its tail is at the origin, then its head is going to be at the point with coordinates 6, 2, 3. Well, of course, we will be moving this vector parallel to itself, so I should show this vector parallel to this. So that's the idea. So this is the displacement vector, initial position of the particle, final position. So it moves in a straight line. And to name this vector r, we need to just position the tail of the vector at the origin. Then the head of the vector, the coordinates of the head, gives us the vector. So vector r then, if we want to write it in ijk form, is 6i plus 2j plus 3k. So now we can go on and get f dot r. So we just multiply corresponding components. We multiply the I components together. It's 3 by 6. Then the j components. Well, the j component of this vector is 0. The j component here is 2. Then the k components, 7 multiplied by 3. We get 18 and 21, which is 39. By the way, assuming that the units are the correct SI units, then the magnitude of this vector would be in newtons. So the magnitude of F is root 58 newtons, and the magnitude of R is root 6 squared plus 2 squared plus 3 squared. Okay, this is the magnitude. So anyway, this works out to 7. Now this would be in meters. So assuming that we're using SI units, so the work done is Newton meters. That's the unit, or joules. So force in newtons times distance in meters. Lastly, we will find the angle between these two vectors. So here's the definition of the dot product of two vectors, and if we rearrange it, we get the angle between the two vectors. So if this vector is A and this vector is B, then A dot B is 1 times 2 plus minus 1 by plus 1 plus minus 1 by plus 2. We have to get the magnitude of A, so we square the components and sum them. 1 squared plus 1 squared plus 1 squared, that's 3. Then we have to get the magnitude of B, 2 squared plus 1 squared plus 2 squared. So it's 4 plus 1 plus 4, that's 9. So here is cos theta, so theta is 101.1 degrees.